Hi there! In this video, we're going to learn why computers use binary in 10 minutes. You probably have heard people describe computers are just a bunch of ones and zeros. While this statement is true, the reality is far more intricate. If you are a software developer with non-traditional background and you are busy with delivering features at work, there probably won't be many occasions for you to fully grasp what that statement truly means until one day you need to figure out what CIDR notation is to set up VPC, to understand the meaning of a column in database that is saved as binary, or to tackle a binary-related algorithm question during job interviews. Today, let's take a brief journey into history to understand why computers are built on this foundation of ones and zeros. We will look at the binary form in history, boolean logic, and the powerful combo of those two things, which leads to the building blocks of computers, logic gates. In upcoming videos, we will explore some practical scenarios to enhance your understanding. Stay tuned. Let's start with binary in history. The binary form has been used as a way to convey information for a long time. Back in the 1820s, Louis Braille developed the Braille code based on the French alphabet as an improvement on night writing. Braille characters are formed using a combination of 6 raised dots arranged in a 3-and-2 matrix called the Braille cells. The number and arrangement of these dots differs one character from another. Binary in Braille code is formed as the raised dots versus the flat dots. Later in the 1840s, Samuel Morse successfully demonstrated how telegraph based on electromagnet can speed up long-distance communication with Morse code. The invention of the telegraph truly marks the beginning of modern communication. What is more interesting is the binary code used in telegraph called Morse code. It encodes text characters as standardized sequences of 2 different signal durations, the dots versus the dashes. This is the binary form in Morse code. After looking at this code, when you hear next sound, do you know what it is trying to spell? Leave a comment if you know the answer. Morse code was originally transmitted as electrical pulses, but later extended to audio tones or visual signals. For example, in this 2014 blockbuster sci-fi movie Interstellar, the main characters communicated with Morse code by setting a small jump versus a big jump of the watch hand as the dot and the dash. Morse code is still widely used in fields such as aviation, military, assistive technology, etc. because of its versatility, efficiency, and low operation cost. NASA actually leaves Morse code on the wheels of Curiosity, the well-known Mars rover, and the track spell out JPL, the name of the laboratory manages the rover mission for NASA. Now that we know the binary form has been used by different coding systems throughout history, and it is simple and efficient to communicate information. But computers cannot deal with human codes. They don't have eyes, ears, or fingers. How do they understand the code? Before we get into this question, let's take a step back and look at Boolean logic for a bit, and you will see how powerful it is when you combine those two things together. Boolean algebra was introduced by George Boole in his first book, The Mathematical Analysis of Logic, back in 1847. It is a branch of algebra, but unlike in conventional algebra where it always deals with numbers, in Boolean algebra the operands refer to classes, aka sets, instead of numbers. There are a few fundamental rules in Boolean algebra. Let's take a quick look. Rule number 1, addition and multiplication are commutative. For example, A and B is the same as B and A. Rule number 2, addition and multiplication are also associative as below. Rule number 3, multiplication is said to be distributive over addition like below. A few more important symbols in Boolean algebra is 1 means the universe, that is everything. and the one symbol can be used with the minus sign to indicate the universe excluding something. 0 means an empty class. Common operations such as AND operation or operation can be summarized in these two little tables. You might wonder, why do we need to learn about Boolean algebra? It turns out that when Boolean algebra is combined with electrical circuitry, for example light bulbs with switches, together they actually make it possible for the design and construction of digital computers. Let's see why. By the way, we will also use those Boolean algebra rules we learned here in later videos. For example, this is a pair of switches wired in series to implement the AND operation. And this is a pair of switches wired in parallel to implement the OR operation. We just use the light bulb wire switches to represent logic, basically the OR and operators, and essentially expressing information with hardware. However, this hardware setup is very simple and it cannot scale well, because the longer the length of wire becomes, the more resistance it has to the flow of electricity. This was a major impediment to long-distance telegraphy, and the solution is to have a relay or repeater system. When an incoming current is used to power an electron magnet that pulls down a metal lever, the lever is used as part of a switch connecting a battery to an outgoing wire. This way, a weak incoming current is amplified to make a stronger outgoing current. Let's look at this example. The fact that relays make it possible for a switch to be turned on and off not by human but by an electrical current, and they can be connected together, establish the foundation of the device that acts as the building block for digital circuits, logic gates. Most electronic devices we use today have some form of logic gates in them. The circuit we just saw is a logic gate called AND gate, and there are a few more of them. Since logic gates such as the AND logic gate we just saw are widely used, electrical engineers have a set of symbols for these logic gates. You are probably already familiar with the meanings of the OR gate, AND gate. The little circle means invert, basically invert the input. For example, the NAND logic gate means not AND. The XOR logic gate, aka exclusive OR, the output is true if and only if its arguments differ. Basically, one is true and the other is false. The buffer gate can be used to amplify a weak signal or add a small delay, essentially the buffer. What's interesting is that you can use a NAND or a NOR gate to create all the other logic. By now, you can probably see how the on and off states of electric circuits are used to express information. You may have thought, why not use more states to express more information? Turns out there were attempts to use ternary 3 states or quinary 5 state system. They are doable. However, the more intermediate states are, the harder it is to keep track, and it gets even worse when transistors change states millions of times per second. The existence of Boolean algebra that only works with true and false value, the simplicity of keeping only 2 states with electricity on and off, and the low cost all contributed to the foundation of ones and zeros that computers are built on. Hopefully, this video has helped you getting a better idea of why computers are a bunch of ones and zeros. In upcoming videos, we will go over how numbers are represented in binary and explore some practical scenarios to enhance the understanding. If you enjoy the content of this video, click the subscribe button so you can receive more content like this in the future. Thank you.